Welcome to the Friday seminar. My name is Miguel Figliosi. I'm a civil engineering faculty, and together with Liming Wang and Jenny Liu from urban planning, we're organizing the seminar this term. And today we have a special guest coming from Chicago, but actually graduated from Portland State, got his PhD, working on transit operations and traffic signals. So we're good to have way back to talk about traffic operations and traffic signals and signal priority. So just because this is also seminar 130 class, don't forget to write your attendance and pass the list. And before you ask, we haven't included the assistant from last week, so don't worry if you don't see that you're missing there in terms of last week attendance. Thank you.
Thank you, Miguel. Good afternoon, everyone. I'm so glad to be back here. I see a lot of familiar faces. For those who don't know me, I graduated, as Miguel introduced, I graduated from transportation engineering last summer, actually spring, and as a PhD student. And now I work for Chicago Transit Authority. And my primary research interest during my PhD study is in public transportation. So, and it's a good opportunity to join a transit authority to really understand how they operate the transit fleet. Okay. So this research is actually part of my dissertation last year about transit signal priority performance evaluation based on empirical data. And this paper we just published in, get accepted, not yet published in a journal. And the co-authors, like me, advisor Miguel Figliosi, and Dr. Bertini, who was a professor here, and he moved to California. So now let's begin the presentation. So transit signal priority, how many of you are familiar with transit signal priority or heard of it? Okay, so a few of them. Okay. So I'll give a brief introduction of what is a transit signal priority. So it is basically a technique that to help transit vehicles to get through intersections, signalized intersections quickly by adjusting signal timing. And usually it has three components. So emitter on a bus that generates a priority request and send a request to the downstream traffic light. And there is a detector at the traffic light receive this priority request and pass this signal to the signal controller. And the signal controller, based on certain algorithm and rules to determine whether or not to grant a signal priority and for how long, and to make the decision. Okay, so the two popular transit signal priority phases are green extension and early green. Green extension means extend the regular green time, and early green means truncate the regular red time and start the green phase earlier. So that's the two most popular phases. And in the signal controller, the algorithm determines how to grant transit signal priority. There can be categorized into three groups. So passive, active, and real-time optimal control. So passive TSP, also called unconditional TSP. It means whenever the detector detects a priority request, the signal will decide to grant a signal priority, regardless of state of the bus, whether it's early or late. And the active TSP means it's also called conditional TSP. So it will, depending whether or not to grant a TSP, depending on the bus, it's late or not, or how late it is. So it's threshold based, and usually the duration of the green extension phase or early green phase is predetermined and constant. For example, every time detect the priority, it will grant 5-second green extension or 7-second early green. So it's always threshold based. And the third category is called the real-time optimal control. So there are a lot of algorithms proposed in this group so the real-time optimal control strategies usually collect more real-time information, like the state of the bus, how late it is, and how many onboard passengers, and from all approaches of the intersection, and also sometimes consider the other private vehicles, what's the queue of the private vehicles, and take all of the information together and make a real-time optimal solution for how long it should be a green tension phase or early green phase. So in this category, the results will always, the green tension or early green phase will be always different from cycle to cycle. So it's a real-time optimal solution. So now why we want to evaluate TSP performance? Because we want to know if it help buses to pass through intersection effectively or efficient. And in the literature, there are categorized into three approaches, methodologies: analytic, simulation, and empirical analysis. The analytic and simulation approaches usually are studies that propose some rules or algorithm to, or TSP algorithm. So it's pre-implementation. So look at what's the potential benefit of TSP. And for the empirical analysis, obviously, it's based on empirical data and do a before and after comparison after the TSP has been implemented, and look at how the affects the bus performance. And usually the performance measures they look at include bus travel time, schedule delays, and headway variability, some reliability performance, and delay for other vehicles sometimes. So, so the problem for the empirical analysis now is we can know that, for example, the corridor level travel time from point A to point B, before TSP was implemented, it could be 14 minutes. After TSP implemented, it could be like 12 minutes. So there is 1 minute reduction, but there are so many factors that may contribute to the 1 minute reduction. And if some study accounted for, after controlling for all other factors, the TSP's contribution may be just 5 seconds or 10 seconds. And sometimes it's not significant. So in the literature, there are various results in terms of TSP's contribution, its effect on bus travel time. So we want to know, even if it's significant 5-second reduction or 10-second reduction, we don't know if the TSP system is maximizing its benefit. Or maybe if every individual intersection is working perfectly, then the reduction will be 30 seconds or a minute. So we want to know how each individual intersection is performing well or not, and how effective are they and how efficient are they. So in the literature, there is a lack of effectiveness and efficiency in TSP performance measure. I don't find any like individual intersection level performance measures. So this actually motivates this study. And another motivation is we were lucky to access 3 key data sources. One from TriMet called automatic vehicle location and automatic passenger count data, and 2 other data sources from the city of Portland, PBOT. We know the signal phase log data, which means we know the start and end time for each phase at each intersection, including red phase, green phase, and TSP phases. And we also know the traffic movement data for each intersection and each movement. Okay, so the research question of this study is we want to know for each individual intersection level the effectiveness and efficiency. And we also want to know the time savings versus the delay for cross-street vehicles, how the TSP affects this performance. And we want to know whether there is a significant difference between green tension and early green phases, and also whether it's different between near side and far side stops. And also want to know if we can identify any problems in the current system and also some potential improvement opportunities by doing the research. So this is a study corridor. Maybe most of you are familiar with Southeast Powell Boulevard, running east and west. There are 12 signalized intersections are operated by the SCAT system, which is the Adaptive Traffic Signal Control System. And there are Route 9 runs along this corridor, and Route 66 runs along this corridor. And you can see there are bus stops in both directions. And to study this performance, TSP performance, I need to introduce a terminology called stop-to-stop segment, which means 2 consecutive bus stops that include a signalized intersection. And so in this corridor, in both directions, we found 6 near-side stop-to-stop segments and 12 far-side. Near-side means the stop is close to the departure stop, and far-side means the signal is close to the downstream bus stop. And here shows where the near-side and far-side bus stop located along this corridor in both directions. So this slide shows all of the identified stop-to-stop segments, their spacings, and the location of the signal in those stop segments. You can see most of them are below 0.2 miles, and most near-side segments signal is close to the bus stop than far-side stop-to-stop segment. So next slide shows general information of the signal timing, cycle length, and green time along this corridor for those intersections. And the green time is for the east and westbound through movement. So the red phase will include the left turn protected phases. So you can see some intersections like Milwaukee 39th and 50th have higher cross-street traffic volume, so they have a longer red time. So talk about the methodology of this study. So we have 3 data sources, and first we integrate the 3 data sources into one called stop-to-stop trip database. So obviously each record in this database will be a stop-to-stop trip. And then the stop-to-stop trip database combined with the SCAT signal loss phase log data, and to generate a performance evaluation metrics. So so let's take a look at what each stop-to-stop trip record attributes. So assume this is a stop-to-stop trip, use a far side segment as example. What we know from this stop-to-stop trip according to the data sources, so which we call it input data. So we know the departure arrival time at the 2 bus stops. We also know the passenger activity at the 2 stops. And we know the signal phase, start time and end time for that intersection. And we know the traffic movement data at that intersection. But what we really want to know is when the bus arrives at the intersection, so that we can measure how effective is the TSP. But from this data, we don't know when the bus arrives at the intersection because we only know the time when the bus at a stop. We don't have timestamps between the bus stop. So we have to come up with a methodology to estimate when the bus arrives at the intersection, so we can calculate all of the following performance measures. So based on the input data, what we want to know to add to the stop-to-stop trip attribute is the probability of arriving at an intersection during green phase, red phase, green extension, or early green phase. And we also want to know the signal delay, and if the bus benefits from the TSP phase, what is the time saving? So all of these are estimated variables. How the methodology estimates this, next slide I will explain this. So on the left side, it's a hypothetical stop-to-stop segment and with the intersection. And on the right side is a time-space diagram. And the horizontal axis are the departure time, are the time for the departure stop and the signal and the arrival stop. And you can see from the signal data, we know all of these phases, start time and end time. And we know that for each bus trip, we know the departure time, arrival time. but what we don't know is how they travel, the trajectory of the buses. It could be this, the trajectory is this one, or this one, or this one before the green phase start. So there are multiple potential trajectories along this corridor. So how do we decide this? So, but first we can, since we know the departure arrival time and the signal phase time, we can draw a feasible boundary. So the bus cannot travel higher with a speed higher than the maximum speed. And the bus cannot arrive at the intersection after the arrival time, right? So we can draw a feasible boundary of the trajectories. And then, based on the observed travel speed information between for each individual segment during different time of day, so we can know empirical distribution. So based on the, so we can input the empirical distribution to understand to estimate the probability of each trajectories. So once we understand, we know the probability of each trajectory, then we can estimate the signal delay and the potential time savings. For example, here is a early green phase. Yeah. So for all the buses arrived during the red phase or during the early green phase, the bus will benefit from this TSP phase, and so we can estimate the time saving. So this is the idea of how we estimate time saving and signal delay based on the probabilistic trajectories. And this is the early green phase example. And next slide is a green extension. So example. So you can see the feasible boundary is different, depending on the different combinations between the departure and arrival time and the signal phase time. So there are multiple feasible boundaries, but we considered all possibilities. Okay, so now let's move on to the performance measures. So there are three key set of performance measures: TSP frequency, TSP effectiveness, and efficiency. So now I want to distinguish between effectiveness and efficiency. Effectiveness is from the perspective of a TSP request. Whenever a bus requests a TSP, what is the result? The probability of benefiting from a TSP phase and the probability or the expected time saving if a bus requests TSP. On the other hand, the TSP efficiency is for each granted TSP phase. So for each TSP phase, whether it is beneficial to a bus request or not, and for each second of the TSP phase, granted TSP phase, what is the time saving for the request? So why they are different, I will give you an example. For example, if a bus requests a TSP, in the passive TSP algorithm, every time a request will trigger a TSP phase. So you will have a very effective TSP request result, but the efficiency is not good because you grant TSP phase every time there is a request. So we want to know how efficient are they and how effective are they. So first, let's take a look at the TSP frequency. So in this slide, it shows on the left-hand side shows the average number of TSP phases granted at each intersection by green extension phase and early green phase. You can see there are more green extension phases are granted than early green phase. And two intersections, like 26th Avenue and 33rd Avenue, there are very few TSP phases granted. And later we talked to the city engineers. They found some TSP settings problem at these two intersections. So in the future, in the following slides, we exclude those performance measures for those two intersections. On the right-hand side, you can see the average number of bus trips pass through the intersection for both directions, and how many of them request TSP and how many of them did not request TSP. You can see about half of them requested TSP. So it shows for all of the TSP requests, about half of them triggered a TSP phase granted. But how effective and efficient are they? I will talk about them later. Okay, so before I start, I want to talk about when a TSP request can benefit from a TSP phase for green extension and early green phase. So let's look at this clockwise. So if a bus will benefit from a green extension phase, the bus really have to arrive at the intersection right during the green extension phase. If you arrive early during the green phase, then you don't benefit from the green extension. You already passed the intersection. If you arrive late, and then you have to wait for red light. So really, if we imagine a random or uniform arrival distribution, then the probability of benefiting from the green extension phase is really this area divided by the whole pipe. For early green phase, it's different because whenever the bus arrives during the red phase, it will benefit from the early green phase. Or even the bus arrives during the early green phase, it will benefit. So early green phase, whenever a bus requests TSP, it has higher probability of benefiting from TSP. But the time saving is smaller. It's at maximum the early green phase duration. But once a bus benefits from green extension phase, it will save the bus the whole following red phase duration. So it's like for green extension, low probability, higher time saving. But for early green phase, high probability but low time saving. So if we assume a uniform arrival rate, and this is a potential result when a bus requests TSP. About depending on the green cycle length, green and red phase split at different intersections for different approaches, this is different. For example, at 39, which has a longer red phase duration, then the bus has a higher, about 50% probability of benefit from the early green phase. Okay, so this is if we assume everything works perfect and our bus arrival rate is uniform. And okay, next. So what are actual outcomes of a TSP request? So it might be that no TSP phases are granted in the cycle when the bus arrives at an intersection, or there is a TSP phase granted, and it could be a green extension phase or early green phase or both granted in a cycle. So this we didn't expect this before the analysis, but in the data we found sometimes green extension and early green phase are granted in the same cycle. So we want to know the breakout of these different outcomes. So this graph shows whenever there is a TSP request, what is the outcome percentage of outcomes? No TSP phase in gray color, and only early green phase or only green extension phase or both green extension and early green phase. And we found we can see much more green extension phases than early green and phases. And we see a significant amount of them are both of the TSP phases, both green extension and early green phases are granted. So now let me introduce a concept of TSP effectiveness. And on the upper right corner is a small time-space diagram. Shows 3 cycles, and the errors are some potential bus trajectories. So here is a green extension example. So whenever a bus requests TSP, the results could be in cycle 1, no TSP phase granted, because the bus may the priority request at the beginning of the green phase, then the signal decide, oh, no need to grant a green extension phase. So could be in cycle 1, or in cycle 3, a bus requests TSP and a green extension phase was granted in cycle 3, but the bus already crossed the intersection. You can see in the time-space diagram, the bus crossed intersection, and then a green extension phase was granted. So in this case, the TSP phase is late to bus A. Or if a bus crosses intersection right during the green extension phase, then it's on time. If the bus arrived during the red phase, then the green extension phase was early relative to the bus. So only when the bus crosses the intersection during the green extension phase is called on time, and the bus will have some time saving because of the green extension phase. So with this concept, we also calculate the results. Whenever a bus requests TSP, what are the percentage of late, on time, and early green extension phases, or no green extension phases? You can see, so the majority is it will not generate a green extension phase, which is a type of bus D, and followed by late green extension phases. A lot of the cases, we found that the bus passed through the intersection, and then a green extension phase was granted, which is not efficient, right? Although the bus triggered a TSP phase, green extension phase, but the bus didn't take advantage of this TSP phase, so it's not an efficient way. So this is for green extension, and let's take a look at early green. So early green, we see more on-time early greens than green extension, because early green phases, the bus has a higher probability of benefiting from early green. So early green phase seems have a higher probability than green extension phase for a TSP request. And now, if we take only the on-time probabilities from green extension and early green phase, this is the actual TSP effectiveness. When the bus requests TSP, like only 10% probability it will benefit from an early green phase, and less than 5% it will benefit from a green extension phase. If you remember the potential result, and this is a comparison, you see there was a big gap between actual and potential results. So that means the system has a lot of improvement opportunity to better serve the buses. And so this slide shows for each bus request TSP, what is the potential benefit, which is called time saving, weighted by number of passengers on the bus. So, for example, whenever a bus requests TSP, there will be expected time saving is 20 seconds, 20 person second benefit from early green, and maybe 13 person second benefit from green extension. And it all varies significantly between different intersections because of the different signal timings, as green and the red split. So next, let's talk about TSP efficiency. So whenever there is a granted TSP phase, it could be benefited to a TSP request within a cycle, or it could be no TSP request within the cycle. And because TSP phase can be triggered by two directions, so we want to know for each intersection, for each granted TSP phases, they are triggered by eastbound or westbound or both, or no request within a cycle. So this is the result. It shows for most of the intersections, east-west are half-half, and some intersections, like 42nd, more from the westbound than from the eastbound. So there is some TSP settings problem they may need to improve. This is for green extension. And for early green phases, also for most of the intersections, they are granted they are triggered by half by eastbound, half by westbound request. But 42nd Avenue, most of them triggered by westbound request. So TSP efficiency, similar slide as previous slide, but now we're thinking about this problem from the perspective of a granted TSP phase in cycle 2 and cycle 3. So cycle 2 is a green extension phase granted without any buses within a cycle. So in theory, this doesn't seem correct, right? But in practice, we see this this kind of cases with a significant amount percentage. And why is that? Maybe because there is a so now we plot the error as a bus request a TSP and pass through intersection. Maybe a bus crossed an intersection, but according to the delay, the bus didn't request a TSP, but actually the bus requests a TSP even though it's early. So that may generate a green extension phase granted, but we can't find any request based on the 30 seconds late threshold. Oh, I forgot to mention that in Portland, the threshold for buses to generate a TSP request is when the bus is more than 30 seconds late. So it could be a bus is 25 seconds late, but it's requested a TSP, and it doesn't show here because in the data, we don't have the emitters data on the bus, whether it's a request or not, but we can only know when the bus is 30 seconds late or not. If it is more than 30 seconds late, we think the bus requests TSP. If not, we think the bus did not request TSP. So this kind of situation, maybe the bus is it's less than 30 seconds late, but requests a TSP. But anyway, so there are two types. Cycle 2, we see a green extension phase, but no request found. And in cycle 3, we found a green extension phase, but also, again, could be triggered by bus A or triggered by bus B or triggered by bus C. And only if it is triggered by bus B, then it is an efficient green extension phase. And it's late to bus A and early to bus C. Okay. And so now we want to know for each granted green extension phase, what's the percentage there we can't find any requests in a cycle, or it's late to a request, or on time to a request, or early to a request. And we found the majority is late to a request. And within the same cycle, but it's late. So there are multiple reasons for this, but we don't know the exact reason, but we think that there is a checkout, so priority request checkout problem with these intersections, which means once the bus passes through the intersection, the detector should tell the signal controller know that the bus already passed, then cancel any green extension phase. But it seems there is a problem in the cancellation of priority request, and that could be a reason that we see so many green extension phases are granted late. So this is for green extension phase. Similarly, for early green phase, so we see more granted early green phases are efficient, which is means on time to bus B, because they have a higher probability of benefit from early green phase. So again, the results always vary from between intersections. So now we want to know another efficiency performance measures, which is time savings versus delay. So whenever a TSP phase is granted, it will create additional delay for cross-street vehicles, right? And for passenger vehicles. For the major street, private vehicles may benefit from the TSP phase, whether it's a green extension or early green phase, no matter the TSP phase is on time or not to a bus. So if the TSP phase is granted on time to a bus, then we will see additional time saving for passengers on the bus. So we want to know for all of the granted TSP phases, what is the average time saving for buses and for vehicles, and compare them. So this chart shows the average time saving, passenger time saving for each granted early green phase. And you can see about, on average, about 100 seconds. Whenever an early green phase was granted, 100 person seconds will be saved for buses. Yeah. And for green extension phase, much lower. Why is that? Because we have so many late granted green extension phases, which makes the denominator too large. So the average time saving is lower. So next slide, we also want to estimate what is the benefit, time saving, and delay for other private vehicles on the street. So now we use the vehicle count information from the database. We know the vehicle arrival rate and volume flow. So we know the arrival rate and departure and the capacity of the intersection. So we can estimate the for each second of green extension or early green phase, what is the time saving and the delay for the side street vehicles and the cross street and major street vehicles. And the results, if we put them together, the result looks like this. So the red bar means the delay for cross street vehicles, and the darker green is the time saving for passengers on the bus, and the lighter green is the time saving for major street private vehicles, assuming each vehicle is a single occupancy. And you can see, and this is for each second of green extension phase. We can see for most of the intersections, the benefit and the time saving and the delay almost equal to each other for most of them, the total benefit and total delay. But if we only look at the passenger time saving on the bus, it's much smaller than the delay to cross street vehicles. So which means under current performance, because we granted too many late green extension phases, actually we just steal some time from the cross street green time and make it for major street green time. It has a less effect on passengers on the bus because we're not using green extension phase efficiently. For early green phase, we can see for most of the intersections, the total time savings is more than the total delay. So because early green is more efficient. And for some intersections, like those small intersections on the right, only the passenger time saving on the bus is more than the delay on the cross street. So it looks like now the current corridor, the signal system, early green is more efficient than green extension phase. So to summarize the findings from this analysis performance evaluation, we found that TSP performance varies significantly across the intersection. So we just so if we look at the very high level and the corridor level, we don't know these individual intersection performance are so varies, so they are so different. And we found that there is a big gap between actual and ideal performance. So which means this TSP system has a big potential for improvement. And for the green extension phase, we see too many late granted green extension phases that have to be reduced. But the result is total time saving almost equal to the total delay. For early green, we see the time saving is more than the delay, which is good. So conclusions, the proposed TSP performance measures can help the transit agency or the city of Portland or any other city to identify problems at the intersection level and identify problem and improvement opportunities at the intersection level and to help them make decisions. although the findings from this study is really site-specific at this corridor, it may be very different at another corridor or at another city. But the whole algorithm, the methodology can be transferable to any city, as long as the city has transit data and transit AVL, APC data, and signal timing data. No matter it's a scat or fixed timing, as long as they have the signal start and log phases. And if they want to estimate the total delay versus total time saving, in considering the private vehicles, then if they just have to have the traffic count data. Then if they have the 3 data sets, then this methodology can be applied everywhere. So, and then we also found that effectiveness and efficiency can be affected by so many factors: the control algorithm, the parameter calibration, and signal detection, or the wireless communication. So all of them could lead to any problems of TSP. So some future work. So if you remember the time-space diagram of the methodology, we didn't consider the vehicle queuing when we calculate the probability of vehicle trajectories, of bus trajectories. So that's one of the future work to provide a more accurate estimation of the vehicle trajectory probability. And also, we found TriMet is archiving the higher resolution bus data, which provide additional information to buses between stops. So every 5 seconds, there is a timestamp of the buses. So with that information, we can know the bus trajectories more accurately than this one. And also, the city of Portland, they have a new data called TSP optical detector data. So at the traffic light, the detector, they have a record when and how strong the TSP request is received from the buses. So with that data, we can verify some of the findings. Why for example, whether when a bus crosses the intersection, the priority request has been canceled or not. So with that data, we can answer that question. So finally, we would like to thank Steve Callis and David Crow from TriMet, and Peter Coons and Willie Rossi from City of Portland providing us the data, and also Track and NISI for sponsoring this research. With that, I would like to take your questions. Yeah.
If an east-west
do you need a microphone? No? Oh, okay. Go ahead.
If an east-westbound bus requests a green extension and north-south bus requests early green, how is that handled at an intersection?
So currently it's a first in, first service, so first come, first service, whichever. But also depending on the algorithm, consider north-south or not. If it is a small street, they will not consider north-south request. I'm not sure for each individual intersection how they program, but most for those 39s, 50s, those major intersections is considering 4 approaches. Which approach comes in first is served which request. Any question? Yes.
I guess it was really interesting to see the variation of the distribution of the effective green or early green and at each of the intersections. Was there anything besides the traffic signal itself, the signal cycle, around including the surrounding areas? Or did any of that have a play in it, or did you look at that at all?
It could be, yeah. There are some other factor affect the various performance across the intersection, and one of the key factor is near side or far side stops, and that's in my research question. But actually we found 3 of the nearsighted segments as 22nd and 33rd, we have data issues, so we can't rely on that data. And the other 3 only remaining nearsighted segments, 42nd eastbound is not performing well. So only 2 samples, we can't really draw a conclusion whether nearsighted is good or farsighted is good. Unfortunately, we don't have enough sample size to answer that question. But I believe nearsighted and farsighted, the stop configuration have a strong impact on the TSP performance. And in the literature, most literature agrees that farsighted stop is better for TSP performance because it has a lower uncertainty of predicting when the bus can arrive at the intersection. If you have a nearsighted stop, there are passenger activities, so you add more uncertainty of predicting the bus when the bus would arrive at the intersection. Yeah.
Are there publications on this apart from your thesis?
This just been, actually last week has been accepted for publication, but it may take a few weeks or months to be available. Yeah.
Where will it be?
TRR, Transportation Research Record. Yeah. Oh, yeah.
So I have a question from one of our online viewers.
Yeah.
And so Lindsay asks whether this is a widely used technology and if it has been used in other cities. Has it been researched in cities with considerably less or lower pedestrian use?
Pedestrian use? Oh.
Just in general. Less people who are walking around.
I know this TSP has been implemented in many cities and also in Portland, many corridors like Barber Boulevard and Powell Boulevard and many corridors. So to answer the first questions, like I said, we've seen a lot of literature comparing before and after of the TSP implementation, how it affects the performance, and really a mixed result. Some corridor see improvement, some corridor no significant improvement, and some corridor, for different performance measures, they have different results. So it's really not like TSP is always good or not. To answer the question in terms of pedestrian, high pedestrian volume, I didn't pay attention to whether the TSP phase affect the pedestrian. I'm not very familiar with how it affects the pedestrian, but pedestrian volumes, for sure, it affects the TSP decision because the minimum walking time, all those may affect the signal logic to decide whether or not to grant a TSP or not and when to grant it.
So
yes,
maybe you can comment on how, if there is any difference at different times of the day with different levels of traffic and different levels of congestion, how that may affect some of the findings.
Yes, different traffic volume really affects the results too. So, for example, in AM, PM peak hour, when we have higher traffic volume in different directions, then we see more. So I didn't show the results, but in AM and PM peak hours, we see more priority requests and more heavier priority TSP phases requests granted. In terms of performance, also varies, really varies from AM peak hour, midday, and PM peak hour. So a lot of dimensions. The performance varies by intersections, by time of day, and by types of like near side or far side stops. So, yeah. Yes.
Would the data you have be sufficient to figure out the percentage of the time that when a bus was granted a TSP request that it actually improved its on-time status? That is, could you tell that it came in 45 seconds late. Its benefit is now it's only 37 seconds late. Is there enough information in your data set to be able to figure that out if someone wanted to?
Yeah, we're able to estimate that. So for those on-time TSP phases, so whenever the TSP phase is on time to a request, then we're able to estimate the actual benefit of the bus, whether it saved the bus 15 seconds or 5 seconds or 3 seconds. For each individual request, we know how many seconds is saved.
You know how many seconds it's saved, but if you look at when it arrives at a subsequent stop, is it actually does it actually sort of realize, you give it a benefit of the signal, does that actually translate into benefit in your on-time status as you go down? Because maybe it got you there early, but you were going to have to stop at the next red light anyway, and so you're still as late.
Yeah, I understand. Yeah, that's a summarized level of how it affects the on-time performance. In this study, we didn't look at specifically on-time status statistically, like over the whole month, how it improved. We didn't look at that, but based on the results, we will think currently it, especially green extension phase, doesn't help too much in terms of on-time performance. And if we look at the aggregate overall in the corridor, the on-time performance, maybe a little improvement because of early green. I just didn't do the statistic of summarize all of the, but.
My question is not whether you did it, but would your data support that?
Yes, it will support, it support, And actually, to do that, we don't really need to join the signal phase log data. Just look at the bus on-time performance improvement before and after.
Well, I'm sort of trying to get to the benefit towards on-time performance, like per extension granted or something like that.
Oh, per extension grant. Oh, yeah, I understand. Not just by looking at how many times saved. Maybe saved 5 seconds, but the bus actually don't need the 5 second time saving. Yeah, I understand. Yeah, so that's a good point to look at. Additional performance metric to add this, like how it improve on-time performance at each individual intersection. Yeah, thanks.
So there is a question of mine about why spending time and energy doing TSP, why Portland implements TSP. So what's the argument for having this system?
So why Portland implement TSP? I'm not sure if I can answer this problem, but in general, TSP is designed to help transit vehicles to reduce transit vehicle delay and improve service reliability. So in the long term, if we can help improve the service reliability, we'll see more increasing in terms of transit mode share and transit ridership, and improve the travel mode choice, more public transit oriented. So why we want to study this? If the city implement TSP and spend money on this, and it's not working so efficiently or effectively, then the investment is not efficient, and so we need to identify what is the problem, make it not very efficient, and to improve it. So this is why the study is motivated, is to really help understand the details, how well TSP is working or not, and try to maximize the TSP's benefit. And another benefit for TSP is it is really a very small investment of improving service reliability compared to other strategies like build a bus-only lane or any other planning strategies. It will cost more, and the TSP really costs small, just some delay for cross-street vehicles, just only by adjusting the signal timing.
Thank you very much.